This CFD training package is prepared for intermediate users of Ansys Fluent software in heat transfer area. The intermediate heat transfer CFD training package has 10 different CFD projects, including comprehensive training movies and CFD simulation files. By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe.
In this project, we will simulate a Heller dry cooling tower. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. Now there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure-based since we are deriving compressible flows. As for the velocity formulation, we have set the absolute format, and as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. Also, as was previously mentioned about the gravity, you can see here that we have enabled the gravity, and the value of gravity is defined to be equal to minus 9.81 in z direction in order to capture the effect of buoyancy forces and changes in density due to the temperature changes. In the appeared window under the Momentum tab, you can see that in front of the gauge total pressure defined for this boundary, the value of 0 is defined. Now in order to extract 2D contour, we first have to define a plane. To do that, we click on Location and then select Plane and accept the appeared window. After that, just like the previous slide, on the low left side of the software window, we select XY plane and set the value of Z to be equal to the value as you can see in this window. After that, we click on Apply and the software will define the plane for us. Now in this contour, you can easily see the temperature distribution in the middle section of our computational domain. As you can easily see, the airflow exiting the Heller construction has higher temperature comparing to the ambient temperature. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate the solidification of molten steel inside solidifying chamber. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. If you expand the fluid under the material section, you can see that 3 phases of air, liquid, solid, and water liquid have been defined here. Now if you double click on liquid solid material in the appeared window, you can see different properties for this material. Now here you can see the mass flow rate of the water liquid entering this boundary is equal to 16 kilograms per second. After double clicking on the controls button, a new window will appear showing you different values for current number and under relaxation factors. The current number is a factor for how fast we are progressing in our simulation process. And for problems with high nonlinearities, we should decrease this current number. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. Now in this slide, you can easily see the molten steel entering our computational domain. Now in this contour, you can easily see the temperature distribution inside our computational domain and how molten steel has entered our computational domain, changing the temperature of the water liquid inside it. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The problem is simulating heat transfer by a radiator inside a room by a transient solver. To simulate the present model, several assumptions are considered. We perform a pressure-based solver. In the viscous model, the standard K-epsilon model has been used. That is a 2-equation turbulence model that allows the determination of both a turbulent length and time scale by solving 2 separate transport equations. The standard K epsilon model is in Ansys Fluent falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard K epsilon model is a model based on model transport equations for the turbulence kinetic energy K and its dissipation rate epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the K epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard K epsilon model is therefore valid only for fully turbulent flows. There is a wall fin that is indicated in this picture and also a wall fin shadow. As the thermal condition of this wall is coupled, so automatically the software will make a shadow wall that all the thermal condition and boundary condition of these two walls are the same. It's just the shadow of this wall. For a better understanding of the buoyancy effect that has been occurred in the simulation, we can check the velocity vector and see the vectors that all of them are upward at the top of the radiator. That shows the buoyancy effect. A summary of the defining steps of the problem and its solution is given in the following tables. The present issue concerns the simulation of a gasoline fuel tank carrying a single-way reciprocating spiral tube passing through the tank. Therefore, the present model uses a solidification and melting module for the CFD simulation by Ansys Fluent software. In the near wall treatment option, we select the standard wall function. Because if the K epsilon turbulence model is used like in this simulation, it is not possible to simulate flow vortex near the walls. So a wall function must be defined, that is a standard wall function for this simulation, to investigate the fluid behavior near the wall. Also, the initial value of the temperature is equal to 253 degrees of Kelvin. That shows the solid phase of the gasoline in the start point. And from the solidification and melting liquid fraction two-dimensional contour, we can easily see that the melting is happening and some part of the gasoline that was completely solid start to melt and change to the liquid phase. A summary of the defining steps of the problem and its solution is given materials in these tables organic as compounds that can absorb and store a large amount of latent heat energy.
In this project, nanofluid flow heat transfer in a heat exchanger containing porous medium is simulated and analyzed by Ansys Fluent software. The energy model is activated and the Spalaret-Alarmas model is activated for solving the turbulent flow. Now if you click on the outlet boundary, you can see that the type of this boundary is defined to be pressure outlet. Just like the previous slide, by clicking on edit button and the appearance of the new window, you can see that in front of the gauge pressure, the value of 0 is defined, which means that the flow will exit our computational domain to the atmosphere. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. And finally, in this slide, you can see the streamlines of the airflow in the middle section of our geometry where the tubes are located. Now, as you can see in this contour, vortices have been generated inside our computational domain, which causes the heat transfer rate to increase. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate a solar water desalination system. In General Setup tab, you will see different dialog box from scale to units. By clicking on Scale dialog box, a new window will appear. In the appeared window, we enable the species transfer in the model section, and in the option, we enable the diffusion energy source and thermal diffusion in order to include the effects of enthalpy transfer due to species diffusion in the energy equation. After that, under the Mixture Properties section, in order to change the material of the mixture, we click on the Edit button. After double-clicking on the method, you will see that a new window will appear, showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order event and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. In the appeared contour, you can see the vortices form inside the computational domain, which was explained before is because of the buoyancy forces and gravitational effect that is available inside the computational domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will validate the data provided by the paper named Numerical Investigation of Air Gap Membrane Distillation Seeking Optimal Performance. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, now for vol boundaries, if you click on Edit and open the settings window for each of them, under the Momentum tab, you can see that the stationary vol motion alongside with no slip shear condition is defined for all of them. Now the only difference is in their thermal condition. For example, by clicking on the first vol boundary, you can see that the thermal condition defined for this boundary is set to be coupled. And the vol thickness for this vol is equal to this specific value where you can see. Now about the heat generation rate, the interface wall between the hot saltwater flow and the membrane act as a heat sink with a value equivalent to this value where you can see in this window, which is calculated according to the relationships of 7 to 9 in the article. Now in this contour, you can easily see the temperature distribution inside our computational domain. As was expected, the upper part, which contains the hot saline water, has more temperature in comparison with the pure water flowing in the lower channel of the geometry. It should only be mentioned that point reports give you the temperature on the membrane boundary, whereas the line reports give you the temperature on the bulk. Now in this slide, we brought to you the table which compares our CFD results with the CFD results obtained by the paper. Now in this table, you can see that two sections of 0.1 and 0.15 are specifically designated, which we have calculated their temperature in previous slides. It should only be pointed out that the results in this table have the unit of centigrade, whereas the result we have obtained in previous slides had the unit of Kelvin. The only thing you should do is to change their unit from Kelvin to centigrade, and then you are able to compare the results in this table together. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will numerically validate the data provided by the paper named Thermal Performance Analysis of Solar Parabolic Through Collector using Nanofluid as Working Fluid. In this slide, you can see that we have extracted figure 5 of the paper, which shows a graph of Nusselt number over different Reynolds. Now in this project, we will be validating the results delineated in this graph. After clicking on the inlet boundary, you can see that the type of this boundary is defined to be velocity. But by clicking on Edit button, a new window will appear in which you can change the settings for this boundary. After double-clicking on the Run Calculations button in the Appeared section under the Parameters part, by just defining the number of iterations, and then clicking on Calculate button, the software will start the simulation process. In order to generate 2D contours, just have to right-click on the Contours button and then select New. In the Appeared window, under the Contours of section, you can select your desired variable. For example, in this slide, we have selected the temperature variable. After defining the variable, we go under the Surfaces section and click on our desired surfaces where we want to see our contours. For example, we have selected outlet in this case. After that, by clicking on Save or Display button, the software will show you the 2D contour. In this slide, you can see the temperature contour on the outlet boundary. You can easily see the temperature changes on the lower section of the outer wall where we had the higher heat flux applied. Now in this slide, you can see that we have calculated the Reynolds number based on the fluid velocity we have applied to the inlet boundary. After that, we had calculated the Nusselt number in our CFD simulation, and we have compared our results with the paper's results. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate a shell and tube heat exchanger with a spiral baffle. Now in the Appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on Display so that the software will show you that part. For example, if you click on the Thermal tab for the baffle walls boundary, you can see that under the thermal condition, the coupled condition is defined, which means that this wall is in contact with fluid on its both sides. After double-clicking on the Residuals button, a new window will appear. In the Appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. Now in this slide, you can easily see the streamlines of the water flow flowing inside a heat exchanger. Now in this contour, you can easily see the effect of baffles causing the water flow to rotate inside the heat exchanger space. Now in this 2D contour, you can easily see the temperature changes from the inlet boundary to the outlet, where the temperature has increased due to the heat transfer between the water liquid flow and the inner tubes. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate the air heat transfer in a porous medium chamber. The present model is three-dimensional and is drawn using Design Modeler software. The present model is related to the chamber, which has several spheres as a porous medium in three different directions. The total number of these spheres is 343. Now if you click on this wall boundary and click on Edit button in the Appeared window under the Thermal tab, you can see that we have selected the temperature thermal condition for this wall, and the value of temperature applied on this wall boundary is equal to 273 Kelvin. After double-clicking on the Initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the zero, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. Now in this slide you can see the temperature distribution inside our computational domain, and as you can see here, the region near the upper surface has a higher temperature comparison with the lower surface. And finally, in this slide you can easily see the velocity changes of airflow inside the porous medium in our computational domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.